Chapter 20. Carnot Efficiency. Applying the laws of physics to the economy and our tax structures. Part 2.
Physics states that in the universe, bodies will seek the path of least action, or in other words, that bodies will follow the most efficient path. We see this in the flow of water, to the dynamics of electromagnetism. Correspondingly, think about people. When someone takes a walk, often they will follow the shortest distance between 2 points, or when driving, use map apps to find the fastest route between 2 points. Now consider the first and second laws of thermodynamics. It is not possible to use 100% of energy to do work without some energy being wasted. Also, it is impossible to convert energy into useful work from a hot reservoir with one single temperature. There must be a difference in temperature for energy to be converted into work. That is, there must be a temperature differentiation. To visualize these concepts, think of an internal combustion engine. That's exactly what a forward-thinking French physicist named Sadi Carnot did. Based on the first and second laws of thermodynamics, Carnot had the insight that it is possible to calculate the precise upper limit of efficiency that any thermodynamic engine can achieve during its conversion of energy into work. Carnot conceived an ideal gas engine operating between 2 environments with 2 different temperatures and formalized the maximum work efficiency of that engine, which we now call the Carnot efficiency, which is negatively proportional to the rate of energy wasted from the total injected energy, or to the ratio of the temperatures of the 2 reservoirs. To see these equations, go to the disruptingtaxes.org website. And so, an engine's maximum efficiency can be determined by the proportional difference of the 2 temperatures. More explicitly, the greater the proportional difference between the 2 temperatures, the higher the engine's efficiency, and vice versa. To visualize the Carnot engine, imagine a gas engine with 2 heat sinks of differential temperatures where fuel is ignited and burned, and cool air is expanded by the injected heat, producing work. The hot air is then cooled down, transferring or wasting the heat away, and returning it to its original state so the cycle can start again. For example, if the lower temperature is 150 degrees C or 423 degrees K, and the higher temperature is 500 degrees C or 773 degrees K, then Carnot's formula states that the highest efficiency that engine can achieve is 45.3%. Similarly, a nuclear engine generating electricity has efficiency in the range of about 37% to 42%. As simple as it sounds, this law of energy work conversion governs all of nature with universal applicability, our human society included. Consider your own life and actions. Whenever a person focuses on a particular task, there is inevitably a certain amount of wasted energy. If a person is washing dishes after dinner, there will be some number of distractions, unnecessary spillage, or some forgotten cup or plate that requires its own separate trip to the sink. Taking the next step, scientists have started applying these laws of physics to the engine of a country's economy. In turn, we now suggest applying these laws of physics directly to the engine of the economy within a government's tax system. Here is the magic. We can use the efficiency of a heat engine test to examine the efficiency of our progressive income tax and corporate tax system to the ABT tax system, and ultimately determine how efficiently each tax system extracts funds from the economy to support the societal and governmental infrastructure. Imagine an economy as an engine. Its efficiency of converting available resources like money or its equivalents, that is, raw materials, intellectual capital, etc., to wealth is analogous to that of a thermodynamic heat engine converting heat to useful work. The 3 key parameters of the heat engine used to calculate the efficiency are 1. Energy supplies, 2. Energy wasted, and 3. Work produced. These 3 parameters have corresponding data points in an economic engine, Specifically, 1. Total monetary resource. 2. Exhausted resource, such as tax collected. And 3. Work or wealth created in the form of GDP, salaries, and assets. In this thought experiment, we will use these same symbols to represent each parameter. The complexity of an economic engine is reflected in a wide range of processes, wherein each element exhausts some fraction of the resource. The minimal exhaustion of a resource will lead to the maximum production of wealth. But according to the laws of thermodynamics, there exists a threshold of resource exhaustion under which the functioning of an engine would be impossible. It is logical to make the conjecture that the analogical energy wasted should be the sum of resource exhaustion by all sub-processes, including taxation of the engine. To differentially examine the effects on the economic engine under different tax systems, we artificially suppress all other process, as they are not sensitive to differences in the types of tax systems, and arrive at the formula for the conditional tax, weighted efficiency, or CTE, which is negatively proportional to the rate of tax extraction from the total monetary resource. To see these equations, go to the disruptingtaxes.org website. In this analysis, the two essential quantities are the amount of tax dollars collected from individuals and companies, and the amount of resources or money injected into the economic engine under each different tax system. With this analogy, we consider the tax dollar, a deduction from the individual's wealth and the company's profits, as energy being removed, exhausted, or wasted by individuals and companies from the engine of the economy. Recognize also that tax dollars are spent to provide and maintain the infrastructure of a country so the economy can operate. Therein, the waste is recycled. It is then axiomatic that a minimal ratio of tax collected to the amount of monetary resources will lead to the maximum CTE of an economic engine, and thereby differentially contribute to the creation of maximum individual wealth across all parts of society. In the CTE analysis, to keep our analogy logically consistent, the amount of monetary resources is always identified as the resource pool from which taxes are drawn. We will here use data from 2019, as it is the last year of traditional economic numbers before the pandemic. Here, the progressive tax system primarily targeted salaries and incomes, which totaled to $11 trillion out of a GDP of $21 trillion, where the average individual tax rate was 27%. This amounted to the collection of $3 trillion, or about 86% of the U.S.'s total taxes collected of $3.4 trillion, where corporate taxes only contributed $400 billion, or 6%. Therefore, this data directs that $3 trillion will be resource wasted, and $11 trillion will be the total resource injected. Applying these numbers to the CTE formula, under the progressive tax system's focus on payroll taxes upon salaries and incomes, the computation results in 72.7% of the CTE efficiency. Now, if we expand the math of the progressive tax system to all taxes collected, or $3.4 trillion over the total GDP of $21 trillion, then the math yields 83.8% of the CTE efficiency. Significantly, the foundational premise of a progressive tax system reveals scientific incorrectness, in that progressive taxes look to collect tax in its engine from the GDP, or a portion thereof, that is salaries, which is the work produced as its injected resources, rather than looking to collect tax from the total resources available, or all money and transactions, in the economy. Taxing only salaries or GDP, both known as work produced in the economy, violates the general principle of a thermodynamic engine, that the energy or resource wasted should be taken from all energy supplied to the engine, rather than being taken from the work produced by the engine. Correspondingly, the progressive tax system leads to both poor efficiency and disorder, as we observed. Now let's look at the CTE of the economy under the ABT tax system. In the ABT tax system, the taxes are drawn from all transactions, money flow, in the economy, rather than from only salaries or the GDP. All transactions in an economy are the closest presentation of the total resources injected into the engine of an economy. So from the outset, the ABT tax starts out on the right foot, consistent with the scientific principles of engine efficiency, quite the opposite of progressive taxes. Again, using the data from 2019, the estimated total transactions for that year were 500 trillion, which can be appropriately used as all energy supplied to the engine. As that estimation was calculated with the goal of collecting enough tax revenue to cover all governmental costs of $5 trillion, a 1% total tax rate, this number will therefore be the energy wasted. Here, the CTE of the economy under the ABT tax system works out to be 99%. This computation indicates the ABT tax has a greater potential to produce a more efficient and equitable economy when compared to that of the progressive tax system. To be sure, this comparison is constrained by the inherent limitations of making a qualitative application from rigorous physics formulism. It is also recognized that engine-class numeric comparisons are relative in nature. Still, under the accuracy of mathematics, one would expect an economy operating with high efficiency, or a small exhausted to total resources ratio or tax rate, will in fact collect a favorable amount of tax revenue. This is only systemically possible with a large numerical base of total resources. The ABT tax system reveals a logically consistent structure that scientifically stipulates its merit, a lower tax rate with a larger base. This insight provides real guidance on how to improve the performance, fairness, and equity of a country's tax system.